Welcome to Every Simple International Academy, and today we are going to be treating the first topic on our PHS 001, which is going to be physical quantities and units. Please, before we dive right in, ensure that if you've not subscribed to our channel, do well to click on the subscribe button below and also on the notification bell so that whenever we drop content like this, you will be notified. Alright, the numbers, let's dive right in. Now we have physical quantities and units, and this concept is coined out from the ideology of measurement. So that's where it comes out from. So one major thing you want to note is that the idea in physics is to deal with physical quantities. That's things you can see and things that you can see should be able to be sized. That's the truth. So when you say they should be able to be sized, that means you're able to know the magnitude of those quantities. Good. So the concept of measurement is all about quantification. So when you hear measurement, measurement is a physical act of quantifying. So it's just about quantification. Your ability to quantify. Quantification, you're talking about knowing the amount. You understand? It's about knowing the amount or the size of a given parameter or the given quantity. The quantity is regarded as a parameter. Good. So now, that's what we mean by measurement. Now, measurement is incomplete if you don't carry it along with a specific basis, which we call units. Good. So the idea of somebody coming to meet you and just letting you know, oh yes, I measured a particular plot of land and the plot of land is 40 or the plot of land is 70, it does not spell well on the idea of the size of that land. So it becomes complete when your measurement is made up of two things. What are the two things? When your measurement has a numerical value, so we have numerical value, that's the numeration of your quantification of measurement, and then it also has a unit. And that's where the idea of unit from this PHS 01 first topic comes in. And what do we say is unit? Unit simply refers to the basis upon which measurement is taken. So when you take a measurement, you want to be able to identify or state the unit from which that measurement is taken. Good. So what are these units? For instance, now I measure a plot of land. Is it meter square? Is it centimeter square? That's in terms of area now, when you start hearing square. Or is it meters when you start hearing length or the distance? So that's the idea. You being able to take note of the what? Of the unit and the numerical value. So when I measure maybe the length of a rod and I'm saying that, oh, the length of the rod was probably 20 meters. This 20 meter here stands for the numerical value and the meters here is representing the unit. All of them give an idea of the size, which is referred to as the measurement. That's the idea, scientists. So this is the foundation for this particular course that we're going to be running. So before we continue on what we are doing right here, let's look at the course outline, which is a guide. As a JUPEB candidate and A-level candidate, you should be able to understand the importance of the course outline that has been given to you for each topic. Now, this course we should be able to define the units, which we've done already. We said that units are the basis upon which measurement is taken, right? And then you should be able to discuss or understand the concept of unit conversion and measurement. We've talked about measurement. We'll still emphasize on the unit conversion. After which, we'll look at method of measuring length, mass, and time, and then we'll talk about basic and derived units before we'll talk about dimensional analysis. All right, good. So good. We've talked about units. Now, unit conversion. The thing here, the idea here is this. We have so many kinds of units for measuring different quantities. When we say quantities, we're talking about physical quantities, physical parameters that have the ability to be sized. Physical parameters that have the ability to give us numerical data. Are you getting me now? These are parameters that are continuous. When you talk about the type of data they are continuous. So therefore, they are measuring. All right, good. So, for instance now, we have meters. For instance, now let's take for instance now, we want to look at the quantity called length. And length, you know that the unit of length is meters. For instance, one of the units of length is meters. You can also measure length in centimeters. So how do you run conversions? The first thing you want to know in conversion is the standard relationship between the two units. For instance, now we know that 100 centimeters is what make 1 meters. This relationship here is called the standard conversion relationship of that unit. So before you convert, you must be able to state the SCR of the unit that you are converting before you now bring out your what? Your converting relationship of consideration. For instance, now we were told that we should convert or express 20 centimeter in meters. We want to convert into meters in meters. What do? You have to first state the SCR. Are you getting what I'm saying now? Which is 100 centimeter represents 1 meter. Then you state the CRC, which is what? 20 centimeter is therefore equals to what? An unknown number of meters we can represent as X meters. Now we have the units there, but the numerical value is unknown. Because we want to know what the numerical value should be in cases where we are representing the units now in meters. So what do you do now? You do your basic mathematics where you cross multiply, and then you have 100 what? 100 centimeter and X meters. You have to be very direct and precise. And here we have what? 20 centimeter dot 1 meter. Here dots represent multiplication. Our case study here is the X, right? Good. So we can divide both sides first of all numerically by 100, numerically by 100. Right? Okay, good. So therefore, 100 cancel 100, 100 cancel, can divide 20 and give us 0.2, right? 0.2. So good. What can we do from here now? We want to know how many X centimeter should be equivalent to 20, X meter should be equivalent to 20 centimeter. We want to know what that equivalent should be. So good. From here now, we can see that centimeter, if I divide both sides by 100 centimeter, centimeter can come and cancel centimeter right here too, right? So we are now left with centimeter here, we can centimeter here now. We are now left with what? X is equal to 0.2 numerically, but we know that the unit here or the unit is what? Is meters. So that means 20 centimeter should be equal to what? To 0.2 meters. So across every parameter or unit that you are working with or trying to convert, this is the standard. You must know your SCR, you must state your SCR, which is the standard conversion for that unit there, and that's the relationship, and you must know your what? Your conversion relationship or consideration, which is what you are trying to convert. Good. And then when you have that, you work with that, you get your answer. Good. And that's how conversion is. The same thing applies to other parameters. Okay, good. Now, we now go into the method of measuring length. Firstly, there are 3 major parameters that makes up the cosmos that defines our existential being in this physical world. And what are they? We have length, we have mass, and we have time. Yes, those are the trinity of existence. I don't go into philosophical concepts here, but here now we know that length here can be measured, mass can be measured as well, and time can as well be measured. Now, when you want to measure the length of a material, you can make use of your what? Of your tape rule, or your meter rule rather. You can make use of your meter rule. You can make use of the vernier caliper. You can make use of the micrometer screw gauge. The micrometer screw gauge. Yes, you can make use of that. So many other things you can make use of. A lot of them like that. If you are measuring your mass, you can make use of your beam balance. You can make use of your beam balance. Yes. You can also make use of the spring balance. the spring balance. Now, one thing I want you to understand is when you're measuring with your spring balance tends to give you sometimes, in fact, basically depending on the calibration system, it tends to give you the weight of the material. But we already know that given that the gravity of our geographical region is constant, 9.8, then from there we can also get the mass. That's why it's still appropriate to say spring balance measures mass. But most precisely or most accurately, it is going to give you numerical value for your weight. Okay, that's fine. Then time is measured with the clock. Yes, and then you know this clock are of different variation. You have the sand clock, you understand? So there are different variations of that clock, but definitely clock. And what is time? Basically, time is just a parameter that helps in distinguishing events. It's just the parameter that helps in distinguishing events. And what is mass per se? Mass is simply the amount of substance present in a body, the amount of substance contained or present in a body. On the other hand, what is length? Length is simply the distance. In fact, to be more precise, because physics has transcended into an idea that cuts across different kind of concepts. So to be more precise, you have to say there that it is the linear distance. So length is simply the linear distance between two points. And by linear, I mean both curvilinear and rectilinear. Are you there now? Alright, very good. So that's that for that. If it's to be a jam lecture now, you need to know the operating system or principle of Vena caliper, micrometer, screw gauge, and all this stuff. But here now we are dealing with JUPEB concepts, so we really are not going to dwell on those. Now, physical quantities, per se, physical quantities can be divided into, now this is where the issue is going to be. The new idea of the classification of physical quantities, believe that they are divided into only two, which is the basic, also referred to as the fundamental quantities, of which there are 7 numbers. And then you have the what? You have the derived quantities, of which they are numerous in number. Why? Because many parameters are still getting derived even today. This concept of science and learning has not ended yet, so there are still many derivations going on even as we speak. All right, yes. This is the old system for classification, but I'm going to add one more system of classification just in case you come across that in your examination, and that's what the supplementary quantities. Yes. Now, brief one. The basic or fundamental quantities. These quantities are quantities that do not have any base of origination. So they are independent quantities. What do I mean? These quantities do not, or let's just say cannot be obtained by any arithmetic, cannot be obtained by any arithmetic or geometric means. Cannot be obtained by any arithmetic or geometric means from other quantities. And what are we trying to say now? Since we cannot get you from other quantities, it simply means that you are independent. So they are independent quantity. Yes, and in biology, we have the rule that nullifies mutualization, saying that everything in the universe interacts with one another. So therefore, if these guys are independent quantity, it means that they do not depend on any other quantity. So therefore, they must interact with something. And that interaction is that what other quantities will depend on them for existence. That's what I'm driving at. So in other words now, who are these quantities that will have to depend on the fundamental quantities for them to exist? Those are the derived quantities. So these guys are dependent quantities. Do you get that now? So these are the dependent quantities. So it's from these quantities now, it's from these quantities you get these quantities. By what? By multiplication or division of one or two fundamental quantities. So here we're saying that what? That derived quantities are obtained from geometrical operations, or arithmetical operations involving one or two fundamental quantities. There are a number of them, I will soon explore them very soon. Now, what are supplementary quantities? That's what I'm driving at now. There was once a period when the supplementary quantities were believed to be part of the fundamental quantities, and even now they have been able to consider the supplementary quantities members of the derived. You see that now? So that's why in this lecture here, I'm rather putting them as a separate quantity on their own for clarity's sake, but making you understand now that the supplementary quantity has a basis for derivation, which I am going to be showing you very, very soon. You know, we said that quantities like fundamental should not be able to derive from any other quantity. So then they place them in earlier concept. They once place them alone on their own, where they were supplementary, just like I did on the body here. But in later discovery, they've been found to be placed under the derived quantities. They have never been a period of time where the supplementary quantities were considered fundamental. That's what I'm driving at. So we have only 7 fundamental quantities. All right, good. Now, the supplementary quantities, what are they? These are the quantities of angles. They are the quantities of angles, and I'm going to explore them first. What kind of angles do we have? We have 2 major kinds of angles. Yes, we have 2 major kinds of angles. What are they? We have the solid angles that we get from 3D shapes, that's 3-dimensional shapes. So we have the solid angles, and we also have the plane angles that we get from 2D shapes. Yes, very good. So we have the solid angles, and then we have the plane angle. Yes. What is the unit of the solid angle? The solid angle unit is measured in steradian, while the plane angle is measured in radian. That's their SI unit. Now, I was saying something about the derivation. Let's look at something here now. Let's consider this a sphere. We have a sphere here now. A sphere. Now from this sphere here, let's imagine that this is a centric point within the sphere. If I should draw a line that comes from the center there to any surface there, to any surface that cuts across an area from that sphere, something like this here now. That now becomes something like a conical region, a conical projection from the center to any region of the surface and covers an area. Yes, the ratio of the area covered and the radius gives you the value for the solid angle. So that's like the derivation of your solid angle. Yes, so what are we trying to say here now? We're trying to say that the solid angle is equal to what? Is equal to area divided by radius. But what about plane angle? That's stuff within the length of arc. If I have a radius like this now, and I have this arc and I continue, we call this thing L. We call it L. That's the length of the arc. You can easily remember the relationship that this place here is the angle that has been cut across, that's the plane angle. And without wasting more time, we easily know that the theta here is usually equal to what? It's usually equal to the ratio of the length of arc and the what? And the radius. Yes. Where does this come from? It comes from the idea that what? That recall that what? That length of arc from mathematics gave you what? Theta over 360 times 2 pi r. And recall that pi is equals to 180 when it comes to angular description or representation of pi. And if I should put that into this place here, I'll be having length of arc, which is L, in this case here, is equal to theta over 360 times what now? Times 2 times 180 times r. I'm representing this as 180, and 180 times 2 give me 360. I'm having n is equal to theta over 360 times 360 r. 360 can eliminate 360, I'm left with L is equal to theta r. If I divide both sides by r, I'll be having what theta is equal to L over r, and that is the derivation of the length of arc. That is like the derivation of the solid plane angle. So you can see now that because plane angle has a derivation, we cannot place them as fundamental. Rather, they are even considered more as derived quantities. Yes, very good, and very that's it. So let's quickly highlight the 7 fundamental quantities that we have. So there are 7 fundamental. There are 7 fundamental quantities. There are 7 fundamental quantities. And what are the 7 fundamental quantities? We have what? We have the first 3, which are the major: length, we have mass, we have time, and what are the remaining? We have luminous intensity. Luminous intensity, we describe how bright light shines, as the flux of the light. We also have what? We also have amount of substance. Then we have what? We have current. We have current, yes. And then your length is measured in what? Your length is measured in meters. I'm writing out the SI units here. So the SI unit is the standard unit for which these parameters are measured. So you have meters there. Then you have your mass measured in kilogram. Okay, yes, we have one more here. Temperature. That's the 7th one. So your time is measured in seconds. The SI unit is seconds. That's represented as S. Then we have your luminous intensity that's measured in candela. It's measured in candela. Then you also have your amount of substance, which is measured in mole. And then current measured in ampere. Temperature is measured in Kelvin. Not degree Kelvin, ordinary Kelvin. This here represents the 7 fundamental quantities from which all your derived quantities will be obtained. Yes. So it is imperative that you have these fundamental quantities in your mind so that you can be able to run and understand the derived quantities and how they are derived, because that's the basis of dimension.